Ordinary least squares regression is one of the most powerful tools we have as applied quantitative researchers. This is because of its relatively intuitive origin and the ease of interpreting the results. Before we talk about ordinary least squares, or OLS regression, let's talk about what regression means in the first place. Regression is tracing the dependence of y on x, or put differently, regression is trying to discover the relationship that exists between x and y. Regression is not necessarily even mathematical, though the implementations we will talk about are. Regression could be done simply by drawing a line that shows how you think x and y relate to each other. The problem with just drawing is that we don't know whether what we've drawn is good or optimal in any sense. This is why we need to turn to mathematics and statistics. In this graph, which we'll use throughout this video, the dependent variable, the one on the y-axis, is demonstration activity, and the independent variable is corruption. So we're wondering, what is the relationship between social unrest and corruption? If we are trying to find a line that not only describes the relationship, but is also the best description of that relationship, then we need to define what we mean by best. The line drawn in the plot looks pretty good, but how do we know there's not another straight line we could stick in there that would do better? We turn to OLS regression as a means for figuring out what is best. In the simplest case, where we have one dependent variable, y, and one independent variable, x, we have an equation that looks like this one. In this case, x is the independent or explanatory variable. It is one of the things that we think helps explain why observations have different values on y. Y is the dependent or outcome variable. This is the variable we're trying to explain. B0 is the intercept, that is the expected value of y when x has value 0. B1 is the slope. It tells us how we expect y to change when x changes by 1 unit. And finally, E is the residual. It's the difference between the value of y that we observe and the value that the model would predict for y. In OLS regression, we choose values of B0 and B1 in such a way that the sum of squared residual values is as small as possible. That is, for each value that we would pick of B0 and B1, we'd be able to calculate the residuals and then square and sum them up. OLS chooses the values of B0 and B1 that make that sum as small as possible. Another way of thinking about it is that OLS chooses B0 and B1 so that the points are on average as close as they can be to the line. The solution is not that complicated, but the coefficient B1 is basically the covariance between x and y divided by the variance in x. In fact, it looks a lot like the correlation coefficient, but with a different denominator that is just the sum of squared differences between x and its mean. The point of means, which is the mean of x and the mean of y, is always on the OLS regression line. So once we know B1, we can figure out B0 by plugging in the means of x and y for the x and y values. Let's take a look at a single case. Here I've highlighted the point for Spain. We can see that the intercept, the expected value of y when x is equal to 0, is around 1.5. It's a bit more difficult to guess at the slope, but we'll figure that out on the next slide. The dashed line connecting the point to the regression line represents the residual. The point at the other end of the dashed line that is on the regression line is what we would predict for Spain. As you can see, not all points are perfectly predicted, and it might be the case that no points are perfectly predicted. OLS makes predictions as good as they can be in the aggregate, but not for any particular point. We'll spend a lot of time talking about this in September, but I wanted to show you what the numerical output for an OLS regression looks like. Here, the values in the estimate column are B0 for the intercept and B1 for corruption. The table contains lots of other information as well that we'll talk about later on. As for what this means, let's look at the equation a bit more closely. Here we see that demonstration activity is equal to 1.5 plus 0.32 times corruption plus the residual. So 1.5 is the intercept and 0.32 is the slope. The intercept of 1.5 tells us what we would expect demonstration activity to be when there is no corruption, that is, when corruption equals 0. The slope tells us that for every 1 unit increase in corruption, we expect demonstration activity to increase by 0.32 points. The range of the corruption index in our data is from 0 to 8.6. So we would expect demonstrations in the most corrupt country to be 2.75 points higher than the demonstration activity in the least corrupt country.